Welcome to our lecture on ring theory. Today we are going to explore a fascinating concept called ring homomorphisms. Imagine playing a complex board game and your friend is playing a simplified video game version of it. Even though the pieces look different, the moves correspond perfectly. In abstract algebra, we often want to compare two different mathematical universes, called rings, to see if they share the same underlying structure. A ring homomorphism is exactly this kind of structural bridge. Let us dive in and see how it works. Now that we have a high-level idea, let us define this concept formally. Why does this matter? Because in mathematics, understanding a complex structure is much easier if we can map it to a simpler one without breaking its rules. A ring is simply a set of elements equipped with addition and multiplication. Suppose we have two rings, R and S. A ring homomorphism is a special function that takes an input from ring R and assigns it to an output in ring S. But it is not just any function, it must respect the operations. If you add or multiply elements in the first ring and then map them, you must get the exact same result as mapping them first and then combining them in the second ring. This brings us to the formal mathematical definition. Where do these equations come from? They are the literal translation of preserving structure. The first equation guarantees that the function preserves addition. The left side tells us to add A and B inside the first ring, then apply the function. The right side tells us to apply the function first, then add the outputs in the second ring. The second equation ensures the exact same rule holds for multiplication. For a function phi to be a valid ring homomorphism, both of these equations must hold true for every single pair of elements in the starting ring. If either rule fails, the structural bridge collapses. Before we move on, let us see this with a concrete visual example. Here we are looking at a diagram of our two mathematical universes. On the left, we have ring R, and on the right, ring S. Notice the elements A and B inside ring R. When we add them together, we get a new element, A plus B. Now follow the arrows which represent our homomorphism function phi. The element A maps to phi of A, the element B maps to phi of B. The crucial part is the third arrow. The sum A plus B maps exactly to the sum of phi of A and phi of B in the second ring. This diagram perfectly captures what we mean when we say the function preserves the structure of addition. Now that we have seen the visual, let us apply this to a concrete example. We are given a function that takes any standard integer and maps it to its remainder when divided by 4. This maps the ring of integers to the ring of integers modulo 4. We are asked to prove this is a valid homomorphism. First, we test the addition rule. We add two arbitrary integers a and b and apply our function, which means taking their sum modulo 4. A fundamental property of modular arithmetic is that the remainder of a massive sum equals the sum of the individual remainders. By substituting our function definition back in, we see that the addition structure is perfectly preserved. Having verified addition, we must now test the multiplication rule to ensure it is also preserved. We multiply the integers a and b together first and then apply our function by finding the remainder of that product when divided by 4. Just like with addition, modular arithmetic allows us to take the remainders of the individual numbers first before multiplying them together. Substituting our function definition back in one last time, we arrive at our final answer. The function applied to the product equals the product of the individually applied functions. Because both operations are respected, this mapping is indeed a valid ring homomorphism. It perfectly translates standard integer math into modular clock math. Let us look at another powerful example, known as the evaluation homomorphism. Here, we are given a function that takes any polynomial with real coefficients and evaluates it at x equals 0. We need to verify if this acts as a homomorphism from the ring of polynomials to the ring of real numbers. We begin by checking the addition condition. We define a new polynomial that is the sum of p of x and q of x and plug in 0. By the standard definition of polynomial addition, evaluating a combined sum at a specific point is exactly the same as evaluating each polynomial individually and adding the results. Replacing the evaluations with our function notation, we see addition is preserved. Half of our proof is complete, so now we must check the multiplication condition. We multiply the two polynomials together to form a new product polynomial and then evaluate it by plugging in 0. Once again, the fundamental rules of polynomial multiplication dictate that evaluating a product at a specific point yields the exact same number as multiplying their individual evaluations at that point. Substituting our function notation back into the equation gives us our final answer. Since both addition and multiplication are respected, evaluating polynomials at a fixed point is a valid ring homomorphism. This allows us to turn complex polynomial problems into simple numerical arithmetic. Now that we have successfully used the homomorphism formulas in two examples, let us understand a fundamental property that arises from them. We are going to prove that a ring homomorphism always maps the 0 element of the first ring to the 0 element of the second ring. This chunk of the proof sets up our foundation. We start with a simple universal fact in the first ring. Adding 0 to itself results in 0. Next, we apply our homomorphism function phi to both the left and right sides. Because the inputs are perfectly equal, their resulting outputs must also be perfectly equal. This crucial step bridges the gap between the first ring and the second ring. Continuing from our setup, we now use the defining magic of a ring homomorphism. Because phi preserves addition, we can split the left side into the sum of the individual outputs. On the right side, we safely add the 0 element of the second ring, which changes absolutely nothing about its value but helps us balance the equation. Finally, we use the cancellation property of addition, subtracting phi of 0r from both sides. This leaves us with our final result. We have successfully proven that the 0 of the first ring is always perfectly translated to the 0 of the second ring. This intuition shows how deeply homomorphisms lock the structures of two rings together. So we have proven how these mappings work. But this brings us to an important question. Why do we care? In mathematics and computer science, we often deal with incredibly complex systems, like massive polynomials or huge matrices. A ring homomorphism allows us to project these complex systems down into much simpler, smaller systems, while keeping the core rules of arithmetic completely intact. For example, in modern cryptography, computers use homomorphisms to perform calculations directly on encrypted data, without ever needing to decrypt it first. If a system is too hard to solve directly, we translate it, solve it in the simpler ring, and use that answer. It is the ultimate mathematical shortcut. Let us wrap up with the most important ideas from today. First, remember that a ring homomorphism is a structural bridge between two rings. Second, it must perfectly preserve both the addition and multiplication operations. Mapping first, then combining, must equal combining first, then mapping. Third, as we proved, this strict preservation means the 0 element of one ring always maps to the 0 element of the other. Finally, these mappings are powerful tools that allow us to study complex algebraic structures by relating them to simpler, better understood ones. You have now covered the absolute foundation for comparing different mathematical universes. Great job today.